So to conclude, now we have Revant Nayar, who is going to use the language of physics to describe different possible causes for market crashes. Revant, please.
Hi, my name is Revant Nayar. I'm CTO of FMI Tech, and I'm going to present on how we can predict crashes using physics. So, suppose we start with the generic SD governing the evolution of your price process. So, there are three parts of this SD. One is the potential term, which is the nonlinear drift term. One is the volatility term, sigma, and the third is the actual noise term, which you see here. So very naively, you can expect that there are three independent ways to make this SD crash without reducing exogenous shocks. The first is that you make the potential term time dependent, keeping the volatility and noise fixed, which should correspond to some kind of critical phase transition. You can make the volatility time dependent and increasing, keeping the potential and the noise fixed, corresponding to a stochastic phase transition. And or you can evolve the noise term in time, keeping the potential and the volatility fixed, which will correspond to a kind of dynamical phase transition, right? And my bold statement is that underneath all the fancy math, most models will fall into one of these three categories. But which one of these really describes real crashes? And for that, let us look at the early warning signals of these three models. Now, for instance, if you have some kind of critical phase transition, without losing much generality, you can write down the following SD, where you expand the potential to cubic order, which gives you some kind of double well potential, where the price before the crash sits near the minimum on the right, and as time goes on, the potential goes from the red one to the blue one to the purple one, thereby increasing the probability that the price will slip into the minimum on the left and induce the crash. But before the crash happens, you can intuitively see that as the potential flattens out, you have increasing volatility. As the price moves more, you have increasing negative skewness. As as the negative moves, the price larger than the positive moves, and you have increasing autocorrelation at lag one because the price takes longer to come back to the minimum of the potential after it has deviated. Now, if you have a stochastic phase transition where you're keeping the potential fixed but you're varying the volatility, then you would expect by definition to see increasing volatility before the crash. You also expect to see increasing negative skewness as the price can sense out more the asymmetry of the potential, but you don't expect to see any of the um, any of the signals of critical slowing down. On the other hand, now if you have some kind of dynamical phase transition where the noise itself is varying, you think of this as some kind of time varying Hurst exponents, and these, as far as I know, cannot be described by PD or SD. But in this case, you do not expect to see any of the previous early warning signals of the crash. Said all you expect to see is an increasing anomalous dimension, which the Hurst and generalized Hurst are actually special cases. And just briefly defining the anomalous dimension, in a kind of dynamical phase transition, the 2 point expectation values can be described by a power law, and this value delta that actually is the power law exponent is your anomalous dimension, and you can invert it to write it in terms of the 2 point expectation value. And my claim is that the early warning signals of the dynamical phase transition can predict bubble induced crashes much better than those corresponding to critical or stochastic phase transitions. So, for that, we take the top 50, what we call pandemic bubble stocks in the last year, which had been inflated and which recently crashed in the last 2 3 months, and we measure the Kendall trend of the anomalous dimension, where the blue is actually the trend before the crash and yellow is at other times. So in most times you don't see any trend, but right before the crash, you will see a positive trend in the anomalous dimension. But you do not see any significant trend in the variance, lag one autocorrelation, or instantaneous frequency before the crash. And in fact, you see the opposite trend in the skewness than what you expect. using either a critical or stochastic phase transition model. So it appears that at least in the recent crash, it was just described by more of a dynamical phase transition rather than some kind of critical or stochastic phase transition. You can apply this to any crash of your choice, of course. And just a bit about FMI tech, we actually develop similar cool physics-inspired techniques to generate alpha in the financial markets. And we also offer investment management services for people who trust physics with their money. Thank you.